Our first topic for this chapter is electric flux, and this is going to be an important idea or fundamental for this chapter because it's this idea of flux that's going to carry us through and be able to apply Gauss's law. Now, flux also will be used when we talk about magnetic fields, and the concepts are the same, so this will carry through to other chapters also. So we have electric flux, and we represent that by the capital phi, and I put subscript E, and it is a scalar that represents the let's say the amount of electric field through an area. And this area is represented by what we call an area vector. So what is an area vector? Well, let's take a plane, a flat plane, and let's draw a vector, and this vector is normal to the surface in all directions. This would be our area vector. It's the normal, is the mathematical term, the normal to the surface. So with this concept, let's look at how the flux is calculated. So here in the top picture, we have the area A, this plane, and we have an electric field going through it. Well, this area, this plane, is at an angle. And so you have the electric field coming through this plane, but there's this angle here. And so if I break the electric field into a component, I'm going to have this perpendicular electric field vector, and I'm going to have a surface electric field vector. And so this perpendicular electric field vector is also in the same direction as the area vector. So now I can see that I have this relationship, and they have this angle theta between the area vector and the electric field vector. So I have a number of possibilities. If I'm just going to draw my electric field with one arrow, if the area is perpendicular to the electric field vector, so this is my E vector, and let's draw the area vector in red. Here's my area vector, which goes in the same direction. I see that this is a maximum when the angle theta is equal to 0. and that means that this plane is perpendicular to the electric field. Now, the other situation is if I have an electric field and the plane is below. Let me redraw that. So I want to keep my colors straight here. So I have electric field, and I have the plane sitting parallel to the electric field. So my area vector is going to be pointing straight up. And this thing wants to curve. It's going to be pointing straight up, which means that there's a 90-degree angle between the electric field and the area vector. And in this case, angle of theta is equal to 90 degrees, and this gives me a minimum phi. And actually, phi is going to be equal to 0 at this point. So let's think about how we can get a scalar value from two vectors. And the first thing you should think of is the dot product. That gives us a scalar from two vectors. So we have phi, our flux, is going to equal the electric field dot area field, or area vector. E vector dot A vector. And if I just want to, since this is a scalar, I can come up with a formula for just the scalar, and that's the magnitude of the E vector times the magnitude of the A vector. And now remember that we said that it was a maximum when the angle was 0. And since we're dealing with something that's rotational, the one trigonometric function that gives us a 1 when it's at 0 degrees is the cosine of theta. Now, if we're talking about a shape, then the flux would be the surface integral with the electric field going through the surface, dot product of differential area. And this would be the differential of the area vector. And in 3 dimensions, this can get very complicated. So we'd have a surface integral of the E vector, and we might have it in coordinates x, y, and z dot differential area vector with coordinates x, y, and z. So you can see that this becomes very complicated. Well, what we're going to find is that this cosine theta is what limits us in using Gauss's law, because there's only specific instances where this is useful. The Gauss's law is useful when cosine of theta is either equal to 0 or 1. Anything in between means I'd have to figure out this angle, which means that my angle has to be either 0 or 90 degrees or 0 degrees. So we have to think about what shapes will help us to be able to do this. What shapes can we get this kind of symmetry? Well, when we think about shapes that will do this, we can think of spheres, and cylinders, oh, I think I spelled that wrong. Oh, and it's an I-N. I really spelled that wrong. Spheres and cylinders. And that's pretty much the only shapes that are really going to help us. So if we can't get any kind of symmetry with spheres and cylinders, Gauss's law will not help us. Now, we have two definitions for positive and negative flux. One for positive, one for negative. So let's say we have the electric field coming in, and we have some area that it's going through, which means that, and it's exiting, we'll put that here. And so that means I'm going to have an area vector pointing out from the surface this direction. So when this angle theta is greater than pi over 2, the flux is less than 0. On this side, we'll have an area vector. Here's our theta less than pi over 2. And in this case, our phi, our flux, is greater than 0. So positive is always considered with the flux going out of the surface, and we determine that going out of the surface is this angle theta less than pi over 2. It's negative if theta is greater than pi over 2. The other point that we need to make and understand, let me create another shape here. And let's say I have multiple electric field lines from outside of this surface, and these field lines penetrate the surface of this shell or this shape and exit. Well, in this case, the change in flux between what's entering and exiting is going to be equal to 0. There is no net flux for the lines that are coming through the shell and exiting. So we need to keep this definition in mind for entering and exiting flux through a shape. Then that's equal to 0. And now we can start to build on Gauss's law and actually be able to make some use of this idea of flux.